My name is Jackson Whittington, and this is my Part D project over Hooke's Law.
So our project is on Hooke's Law. My name is Allie Dehart. I am in a group with Ashley, Colby, and Jackson.
My name is Ashley Swansea, and I am going to be pursuing a career in radiology or sonography, and this is my presentation on Hooke's Law.
My name is Colby Swansea. I'm majoring in instrumentation, and this is my presentation over Hooke's Law.
Designing a suspension system for prosthetic limb that needs to absorb shock when walking or running is the problem that I chose. You would be using Hooke's Law, which F being the force from impact, like stepping down, K being the stiffness of the elastic material, and X is the amount of stretch or compression. By adjusting K and measuring X, you can fine-tune the system to absorb shock efficiently without it being too stiff or too loose. This will ensure comfort and safety.
Relevance of a problem. Hooke's Law relates force to deformation in buildings, allowing engineers to predict how a structure will bend or compress under stress, such as from weight, wind, or earthquakes, without permanent damage. Using F equals Kx, F is force applied to a structural element, a beam. K is spring constant or stiffness of the material. Resistant is to deformation, and X is displacement of deformation, how much the material stretches or compresses. K will tell you how stiff the material is. High K means the material is stiff like steel, and low K means it's flexible like rubber. If you know the force and stiffness, you can solve for X to find the deformation.
As far as the relevance of the problem goes, Hooke's Law matters a ton as far as racing goes. Basically, you can use F equals K of X to see how much the spring either compresses or just based on how stiff it is. Every spring in racing, matter of fact, has a certain weight. You have like 350-pound springs, you have 980-pound springs. They're all over the place, all different lengths, sizes. It's kind of cool. So understanding this F equals K of X, it can pretty much tell you what a softer spring or stiffer spring does better or worse for a car. So if you have a stiffer spring, you're going to have more grip, but you're going to eat up your tire more, versus if you have a softer spring, you're not going to eat up your tire near as much, but on the flip side, you're not going to have near the amount of grip.
Bridges are an example of Hooke's Law. There is only so much that concrete can hold before it starts to bend and break. The construction workers will not let anyone drive on a new bridge for a couple of weeks after the concrete is poured because it is going to move and shift during that time. This is why constructing roads takes so long.
The benefit of someone understanding prosthetic limb suspension is going to allow engineers and medical professionals to create a more comfortable and responsive prosthetic limb by predicting how elastic components will behave under force. Mastering this is going to encourage deeper thinking about how material properties affect biomechanics, opening doors to smarter, more adaptive technologies in healthcare and rehabilitation. Some of the skills that's going to be gained by this will be analytical thinking by applying physics equations to real-world biomechanics, physics and engineering skills, and biomedical skills. Related problems that you could tackle next would be like shock absorption in prosthetic feet, joint mechanics in prosthetic knees or elbows, and material fatigue and durability.
Benefits of a problem. Using this formula will help engineers to design safe buildings that won't bend too much under stress. It will help them to choose the right materials for different parts of the structure and predict how structures respond to force like wind, weight, or earthquakes. Skills gained by solving this are analytical thinking, engineering insight, and problem solving. Other problems that can be tackled are bridge designing and load distribution, earthquake, resistant buildings, and spacecraft and satellite components.
So what is the overall benefit from understanding this problem? Well, if you understand this F equals K of X, or just the entire spring problem in general, you can better understand how much softer or stiffer of a spring you need, how much longer, how much shorter of a spring you need to better it. Adjust the car to what the driver likes. This can also give you a more clear idea on your sway bar tuning, your shock adjustments, your ride heights, just things like that. It goes way past just the spring stiffness. And overall, you just get to better know your car, how it responds on certain parts of the track. You know exactly when it's going to do what and where it's going to do what.
People know how much weight certain materials can hold. Another good thing is that people know how long the structure will last, given that there is not some earthly effects to it. We are also now able to cross bodies of water by car and train. Finally, we can get goods from another country and states that require crossing bodies of water.
The problem of designing a prosthetic limb suspension system using Hooke's law was developed from scratch by blending human needs and physics properties. Using Hooke's law for a prosthetic limb suspension isn't too simple. It is a practical foundation. The equation may be basic, but applying it to human biomechanics makes the problem complex, impactful, and deeply useful. The prosthetic suspension problem isn't too difficult because Hooke's law gives a clear, manageable framework, simple enough to apply yet powerful enough to guide real-world design. Writing a unique problem was difficult because I had to balance originality with clarity and usefulness, and I avoided making it too simple, too complex, or irrelevant, so it stayed practical and meaningful.
Development of problem. Hooke's law started as a spring experiment and grew into a universal tool for designing safe and strong structures from bridges to skyscrapers. The problem is not too simple to be useful because it scales up to complexity. What starts as a spring equation expands into predicting skyscraper sway, bridge survivability, and earthquakes resistance. It is not too difficult to be useful because Hooke's law uses a simpler linear formula, F equals Kx, that anyone can learn and apply. Difficulties of writing a brand new unique problem is trying to balance originality and clarity and avoiding overcomplication. One thing I avoided was using vague or unrealistic scenarios.
So this problem, the whole entire spring problem, was developed on the fact that spring compression is 100% proportional to force. Using F equals K of X, you can, in the car's corner weight, it's possible to predict your maximum ride height, your suspension movements, things like that, whether it's just your rear end, your shocks, your springs, all kinds of different things play into this. The math is actually relatively simple, but it breaks it down into three categories between force, stiffness, and compression, and ultimately letting your entire crew more, quickly tune the car to your likings without complicated physics like damping equations or motion ratio calculations.
This would be an ongoing issue for anyone who was traveling anywhere, whether they are going one way or another. If we did not have bridges, we would not have a way to get to the other side of the freeway. This problem is an ongoing issue between Beaumont and Houston because they are working on making I-10 wider and nobody can turn around because there are no bridges.
One way that my problem of prosthetic limb suspension stands apart from textbook problems is the spring here is part of someone's body experience. The elastic components in prosthetic sleeves or liners must 1. Absorb shock during walking or running, 2. Maintain secure attachment without discomfort, and 3. Adapt to different body shapes and movement styles. My brand new unique problem differs from common problems like real-world relevance with human impact. Common problems involve ideal springs, carts, or weights in sterile lab setups. My problem applies physics to biomedical engineering, directly affecting comfort, mobility, and dignity for real people using prosthetics. Steps that made this problem unique: instead of using a generic spring, I used prosthetic limbs. I connected Hooke's law to joint movement and shock absorption. This is an open-ended exploration. This problem goes above and beyond common physics problems because it has a real-world impact on people, making it personal and purposeful.
Uniqueness of problem. My unique problem transforms Hooke's law from a simple spring equation into a powerful tool for designing structures, while common textbooks problems often say abstract and predictable. My problem shows how engineers predict deformation, choose material, and design safe structures, while textbooks focuses mainly on calculations, not broader engineering applications. By adding real-world context, material variety, and safety limits, my problem transforms Hooke's law from a simple spring exercise into a more powerful tool, understanding how buildings and bridges stand strong.
So what makes this problem so different is the fact that this is almost 100% performance based on a race car. And if you go online, you're not going to find a performance based race car spring problem unless that's exactly what you're looking for. I mean, it affects the entire geometry of the rear end, even the front end. If you can understand that geometry, you'll be one of the fastest people in a race car to ever sit down in a race car. I mean, it affects your entire ride height, your weight transfers, your handling, your balance, every little thing. It's crazy to think that all of this comes out of a simple F equals K of X formula.
This picture shows the plans for I-10 in Beaumont, Texas. This is unique because it directly affects a lot of people because they use this quite often.
This graph here is going to show a linear relationship between force and displacement in prosthetic limb suspension systems based on Hooke's law. Materials with higher stiffness are going to require more force for the same displacement, and it's going to impact the comfort and stability. Some of the key data points. So I'm using 3 different materials. Material A is a soft gel. This is going to require less force for the same displacement, which is more comfortable but less stable. And then material B, the medium polymer, is balanced force and displacement, which would be for moderate comfort and support. The material C, the rigid composite, requires high force for small displacement, which is very stable but may reduce the comfort. The linear increases in force with displacement means that stiffer materials, a higher K, is going to resist movement more. This is going to affect how the prosthetic limb feels during walking, running, or even standing. Softer materials absorb shock better, while stiffer ones provide control and precision.
Visual for problem. Here is a clear visualization of how displacement changes with applied force for steel, concrete, and wooden beams. This data shows that Hooke's law creates a linear relationship between force and displacement, while stiffness introduces an inverse relationship. These patterns explain why steel beams barely bend, concrete flexes, and wood bends a lot.
So this visual should give you a more of an eye to see how the spring force is perfectly linear as compression increases. I mean, you can see it on the little data points. They're all just in a perfect straight line pointing upwards. I mean, it shows a consistent slope. Spring behavior's very, very predictable. It's not like your regular quadratic or exponential relationships. It stays 100% strictly linear.
This table is from 2020 about the bridges and their conditions based on the national average. According to the table, the state of Texas has some pretty bad bridges.
Reasonable variables that are involved in this solution process. F is for force applied to suspension system measured by newtons. X is displacement for how far the material stretches or compresses measured in meters. K is the spring constant for the stiffness of the suspension material measured in newtons per meter. U, the elastic energy that is stored in the material during deformation measured in joules. You have stress for the pressure on the limb interface measured in pascals. You have strain for relative deformation of the material, which is unitless. Change in length for the amount the material stretches measured in meters. Original length is for the starting length of the material measured in meters. And then Young's modulus for material stiffness under stress measured in pascals. Constants that you might use: gravitational acceleration if analyzing vertical loading. Material-specific spring constants depends on gel, polymer, or composite use. Standard limb mass for modeling average force during movement. Units explained are newtons, how hard the limb presses or pulls. Meters measures displacement, how far the material stretches. Joules measures energy stored relevant for shock absorption. Pascals measure pressure, important for skin comfort and safety. And unitless strain, ratio of stretch, which helps compare flexibility across all materials.
Formula for problem. Some of the core formulas will be F equals Kx to find stress. It will be K equals EA/L. Some of the variables: F equals applied force, which is newtons. X equals displacement, which is meters. Some of the material constants, geometric constants for a given design, safety or design constants, and mathematical constants.
So as far as the formulas go, there's a handful of different ones, but the main one you're going to use is F equals K of X or K equals F divided by X, in which K equals F divided by X helps you determine your spring stiffness, while F equals K of X helps you calculate the needed force to stretch or compress the spring. Another one that you'll use, nowhere nearly as common as those two, is either W or U equals 1/2 kx squared, which comes from the area under the force versus displacement graph that I showed over here. All variables in units like force in newtons, displacement in millimeters or even meters, and energy in joules, they all pretty much tie together to describe, I guess, how the spring stores and releases energy in a more predictable, more measurable way, I guess you could say.
Here are the formulas needed to find the solution to the problem for these bridges.
So the solution for the problem, I did provide a solution process for for analyzing the prosthetic limb suspension using Hooke's law, and I used comparing 3 different types of materials again. Same 3 types of materials as I spoke of earlier: the soft gel, the medium polymer, and the rigid composite. And then I provided your step-by-step calculations. So for the first step, the softer materials are going to require less force to compress, which may feel more comfortable by offering less control. Second step is is more energy is stored in stiffer materials, which can improve shock absorption, but may feel rigid. And then you've got your step 3. This is basically the higher stress is going to cause discomfort on your skin or skin breakdown, especially for sensitive users. The solution is going to show how material stiffness directly affects force, energy, and stress in the prosthetic suspension. Softer materials may be better for comfort, while stiffer ones offer more control and energy return or the shock absorption. The ideal choice is going to depend on the user's preference and activity level, their limb sensitivity, and their lifestyle.
The solution for the problem. Simple scenario, handrail tension cable. Think of a small pedestrian bridge with a handrail made from a tension cable. We will only use Hooke's law, F equals Kx. The setup is applied force, 1,000 N, someone leans hard on the rail. Cable stiffness, 200,000 N/M, typical small steel cable segment. The goal is to find the stretch of X. Hooke's law, X equals F/K. The compute, X equals 1,000 to 200,000 equals 0.005 M. We're going to convert 0.05 M equals 5 millimeters. The result, the handrail cable stretches 5 millimeters under a 1,000 N push, meaning 5 millimeters is small but noticeable, increasing stiffness. Thicker cable or shorter span would reduce that stretch. More force will mean more stretch, and more stiffness will mean less stretch.
So as far as the solution of the problem goes, it looks like a lot. It is a lot. It's relatively easy to explain. For the most part, it's self-explanatory. Just plugging in your numbers that you know, your givens, everything. It's really, really hard to mess this up. So I just took, just as an example, a 350-pound spring, pound per inch, whatever you want to call it, and compressed it 2.8 inches under the entire car's weight, which created about 980 pounds of force. When it hit a bump, the spring compressed to 4.3 inches total. It caused the force to jump, say, to 1,505 pounds. Also, I calculated the energy stored in the spring. It goes from about 155 joules at ride height, which is your maximum ride height, to 366 on the bump, showing pretty much how quickly the load can build and the spring compresses. After you take through all your conversions of the units that you find your masses, your natural period will come out to about half a second.
Each 18-wheeler is approximately 80,000 pounds. The bridge is approximately 116 feet wide, and there's 5 axles per 18-wheeler. The bridge is approximately 261 feet long.
So for verification of problem, I did the check for each step, the force calculation check, the energy storage check, and the stress check, and I provided some information here for the three materials that were compressed by 3 centimeters. So for the first step, these values are reasonable. The forces are in newtons, which is the correct unit for mechanical force. And the range for each one matches what would be expected for soft to rigid materials under small displacements. Step 2, the energy storage check. These values are also reasonable. The units are measured in joules, which is used for energy. And this means that the energy increases faster than force. Then for step 3, the stress check. These values are also reasonable. Units are in pascals, which are used for pressure. The range is within safe limits for skin contact in prosthetics.
Verification for problem. Formula: X equals F/K. Calculation: X equals 1,000 / 200,000 equals 0.005 m. Conversion: 0.005 m equals 5 millimeters. Result matches the expected stretch. The unit check: X equals F/K to N/N/M equals M. Displacement is correctly in meters converted to millimeters for clarity. Range of possible answers. If force doubles, F equals 2,000 N times, or X equals 0.010 M equals 10 millimeters. If stiffness doubles, K equals 400,000 N/M, X equals 0.0025, and M equals 2.5 millimeters. It shows a linear relationship with force and inverse relations with stiffness. Reasonableness: a 5 millimeter stretch under a strong 1,000 N push is small and noticeable. Values in the range of a few millimeters are realistic for pedestrian bridge handrail cables. The value to project topic: it demonstrates Hooke's law in a simple real-world bridge scenario, shows how material stiffness and applied force directly control cable deflection, and provides clear design insight. More force is more stretch, more stiffness is less stretch.
So to help verify this, and a lot of it helps being a race car driver myself, you can see on this little graph here, the force values, they increase linearly with compression, and the energy rises quadratically, which is exactly physically how a spring is supposed to behave, strictly based on your weights. Things like your spring rates, your forces, your stored energy, all follow within realistic ranges for race car suspension systems as well, which once again I can verify just based on experience. Finally, the calculations confirm consistent units and realistic behavior, showing the model quickly does reflect how a race car handles and acts in the real world. It's all, like I said before, performance based. It gives you a better understanding of your load transfers, your balances, and ultimately just your entire spring behavior, car behavior, whatever.
In conclusion, there can be 13 to 26 18-wheelers at a time on the bridge at one given time, based on the guesstimate measurements of the bridge and the strength of concrete. The approximate strength of the bridge is 2,080,000 pounds.